TransE treats every relation like a translation, so inverse and symmetric patterns can collapse. PyKEEN lets us test RotatE on the same graph and measure the recovery with filtered MRR. You'll evaluate RotatE and TransE across symmetric, inverse, and compositional relations with filtered MRR and hits at 10, then predict top tails on the weakest TransE slice. I'm Professor Pi, teaching AI foundations with simple Python. Knowledge graph embedding models turn graph structure into vectors so we can predict missing links. People use them for data curation, recommendation, and schema discovery when relationships matter more than raw text. The challenge is geometry. TransE moves points by a fixed vector for each relation. That is simple and fast, but when relations are symmetric or invertible, the translation can collapse things together. RotatE rotates embeddings in the complex plane, which lets it express symmetry and inversion without forcing a single zero vector to explain both directions. We need two things: a compact dataset that clearly exposes symmetric, inverse, and compositional patterns, and a fair comparison so both models see the same triples and get the same training budget. That way, any gap is geometry, not data or randomness. We will build a tiny PyKEEN toy graph. Train both TransE and RotatE with the same settings. Compute filtered ranks and aggregate MRR and hits at 10. Then turn the weakest TransE slice into a concrete top-tail prediction to make the failure mode visible. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. This snippet builds the smallest PyKEEN graph we need for the comparison. The toy data keeps the pattern visible. Sibling goes both ways. Parent and child point in opposite directions, and near is implied by a parent living in a city. Triples factory, from labeled triples, turns those readable strings into the integer IDs PyKEEN models train on. We keep triples as the labeled source of truth because later snippets use it for filtered ranking. The output confirms the graph size before any model training starts, so we know exactly what data both models will see. With the graph ready, train both models under identical conditions, so any gap is about model geometry, not data handling. This example trains TransE and RotatE through the same PyKEEN pipeline call. The important control is shared. Both models get the same TF, embedding DIM, training budget, seed, and CPU device. That makes the comparison about model geometry, not a hidden data or runtime difference. Num epochs is the main knob here. Increasing it gives the models more chances to fit the toy graph, while decreasing it makes the demo faster but noisier. The output shows the two trained PyKEEN runs are ready for the same downstream ranking checks. Training yields scores, but scores must become ranks under filtered evaluation to be meaningful for link prediction. This code turns PyKEEN scores into the rank a link prediction viewer actually cares about. Predict target scores every possible tail for a fixed head and relation. Here's something like Bob sibling ? The known set implements filtered evaluation for this tiny tutorial. Other already true tails are removed, while the target tail stays in the list. That prevents a model from being punished for ranking another known true triple highly. The output shows the filtered rank of AN for TransE, which is the raw ingredient behind MRR and hits at 10. Aggregate metrics hide where a model fails, so we slice by relation pattern and inspect each kind of query separately. This snippet exposes the failure mode that aggregate scores can hide. Pattern cases names one representative query for each relation pattern. Then bypattern converts its filtered rank into a compact pair. MRR first, Hits at 10 second. Because TransE represents a relation as a translation, symmetric relations create pressure for the translation to behave like zero, which can make false self or nearby entities competitive. RotatE has a different geometry, so the same slicing can reveal whether that pressure is reduced. The output shows TransE's weakest visible pattern, making the next prediction step targeted instead of random. Now that we know which slice TransE struggles with, we will produce concrete top-tail predictions from that exact query and compare them to RotatE. This example finishes the mini baseline by turning the weakest TransE slice into an actual link prediction. Best tail calls PyKEEN predict target for each trained run, sorts by score, and returns the top candidate tail. The case comes from pattern cases weak, so the demo follows the evidence from the metric slice instead of cherry-picking a new query. If TransE's translation geometry struggles on the selected pattern, its top tail may differ from the gold tail even when the aggregate run looked acceptable. The output puts the gold answer beside each model's top prediction, making the geometry issue concrete. If you move this toy into a real dataset, the mapping is direct. Replace the small triples file with a domain dump. Keep the same evaluation flow, and use the slice logic to find relation types where translations fail. That directs effort to the relations where the geometry matters most. In short, RotatE and TransE are both embedding models that predict missing links by scoring candidate tails. Use this comparison when you suspect symmetric or inverse relations will confuse a pure translation geometry. One caution: small synthetic graphs teach geometry, but not production noise, so scale tests are still required. A practical next step is to tune embedding dim and num epochs for both models on a mid-sized benchmark like FB15K237, and re-evaluate filtered MRR by the same pattern slices to see if capacity or training length changes the geometry story. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.